Today I'm going to be talking about intermolecular forces, or forces between molecules. The first type of intermolecular force is van der Waals, which includes London dispersion, dipole-dipole, and dipole-induced dipole forces. London dispersion forces are between two nonpolar covalent molecules, and they're the weakest of all types of intermolecular forces. It's caused by an instantaneous dipole and an induced dipole based on the position of the moving electrons. The electrons are attracted to both their own nucleus and the nucleus of the other molecule it's interacting with, so it forms instantaneous dipoles. The more electrons, the more polarizable, so the higher the atomic number, the stronger these attractions. These instantaneous and induced temporary dipoles are weakly attracted, but they're constantly forming and breaking, so it causes there to be a constant state of attraction. The next type is dipole-dipole forces, which forms between two polar covalent molecules. The positively charged portion, or delta positive, and negatively charged portion, or delta negative, are attracted to each other. And it's a very common intermolecular force because polar molecules are very common. This example is between two hydrochloric acid molecules. The next type is dipole-induced dipole interactions, which occurs between a polar molecule and a nonpolar molecule. The nonpolar molecule is the temporary dipole, while the polar molecule is the permanent dipole. The positively charged portion is attracted to the negatively charged portion. The next type is hydrogen bonding, which is the strongest form of intermolecular forces. This causes materials containing hydrogen bonding to have abnormally high melting and boiling points. Hydrogen bonding is actually a type of dipole-dipole interactions, but they're about 30 times stronger than the ordinary ones, so they're usually classified as a distinct type of intermolecular force. Hydrogen bonding only occurs between hydrogen and fluorine, oxygen, and nitrogen. This is because of Coulomb's law equation depicted here. Hydrogen is delta positive, and fluorine, oxygen, and nitrogen are all electronegative. This causes Q1, Q2, or the partial charges, to be very high. Then, hydrogen, fluorine, oxygen, and nitrogen are all very small elements, causing R squared, or the size factor, to be very small. A large numerator divided by a small denominator causes a large number, which is favorable for hydrogen bonding. This occurs between two polar molecules, and it's extremely important in a biological sense for the secondary structure of proteins, nucleotides in DNA, and water. The third type is ion-dipole interactions, which occurs when an ion encounters a polar molecule. The charge of the ion, in this case delta positive, determines which side of the polar molecules is attracted to it. In this case, it's delta negative. The cation attracts the partial negative side, and the anion attracts the delta positive side. It becomes stronger as the charge on the ion increases, or as the magnitude of the dipole of the polar molecule increases. This example depicts a sodium cation and polar water molecules. The last type of intermolecular force is ionic forces. These are also known as ionic bonds because the electrons are completely sequestered by one atom, creating ions. So there is no distinction of the ions of the same molecule or ions of the nearby molecule. This causes ionic forces/bonds to be in a gray area between intramolecular and intermolecular forces. Ionic bonds occur between two ionic compounds, and it's the strongest kind of intermolecular or intramolecular force. It's formed by electrostatic attractions of opposite charges. This example is the NaCl crystal lattice.